everyone. Welcome to the webinar on natural gas processing. I take this opportunity to welcome today's expert, Dr. J.K. Srivastav, sir. Sir has 40 years of experience in oil and gas industry, mainly in domain of gas and condensate processing, quality control and evaluation of hydrocarbon solvent, technology of crude oil production. He has published more than 10 research papers in international journals. It is an honor and privilege for us to have you, sir. Now I am handing over the session to you, sir. Please, sir.
Thank you. Thank you. Hello.
Yes, sir. Yes. Continue, sir.
Okay. Good afternoon to all of you. As of now, I can't exactly see who are the audience, but I suppose you are all there. So, as introduced by Madam, I have experience in the ONGC for more than 35 years, out of which I had the privilege of working at process plants of Uran and Hazira. So, you know, these two process plants are the largest oil and gas processing plant. So I have the experience of working at Uran plant, where the entire production of Mumbai High and Hira field is processed. And another one at Hazira plant, which is the largest sour gas processing plant in India. So I'll be having my presentation agenda on natural gas. I'll try to give an overview of the natural gas processing, and my agenda covers first and foremost about natural gas. What is the natural gas? What is its composition in general? What is the typical composition of natural gas of the largest gas field of India, that is South Basin? Then what is the composition of processed gas, which is flowing to the, you may be knowing, Hazira, Vijaypur, Jagdishpur line, HVJ pipeline. Then what are its general utilization? Then production and consumption of natural gas in India. Then PNGRB regulations on gas quality specifications for long distance pipeline transportation. This is a very important and very vital. PNGRB stands for Petroleum and Natural Gas Regulatory Board. It is Government of India regulatory agency, which defines various aspects of cross-country pipelines, where what kind of a product can be flown, what could be their quality specification and all. Then basic thing, why processing? Then what are the various process modules? And I'll be natural gas and condensate processing with a reference to Hazira plant, because it is one of the largest gas processing plant in India, where I will briefly sort of covering gas receipt and separation, then gas sweetening, then gas dehydration, then LPG extraction, then condensate stabilization, then dew point depression process, then sulfur recovery from acid gas. Then first, let us begin with what is natural gas. Natural gas, as the name suggests, is the gas produced from geological formations from Mother Earth. You must have heard about oil wells, gas wells, which are drilled, and ONGC is basically engaged is the exploration and E&P company, which is engaged in exploration and production of oil and natural gas. By saying natural gas, we mean that it's not produced by any refinery or any industry. It is what is being produced from the Mother Earth, from geological formations. And broadly, there are three distinct groups. One is a non-associated gas, that is that occurs in the conventional gas fields. For example, in Mumbai High, there is a large field that is called Basin field and Tapti field, which are gas fields where they are producing predominantly gas only. Then associated gas that occurs in conventional oil fields, like in Mumbai High, Hira. These are the fields where the crude oil is being produced, and along with the crude oil, gas is also being produced. Because no crude oil can flow until unless it has a gas dissolved in it. So whatever gas at the surface is releases from the crude oil, that is what we call is associated gas. So that is these are the fields like Mumbai High and Hira field, which are oil fields, and they are producing both oil and gas. Then unconventional gas, you may have heard that coal bed methane, like in Bokaro and other things, by fracking the coal beds, they are getting methane basically. Then shale gas in a very nascent stage in India, not any success so far. But you may be knowing America in the year 2014, they have a huge success with respect to shale gas, and there they surpassed the largest producer, surpassing the Saudi Arabia. So America has a large, USA has a large shale gas production field. Then gas hydrate, this is also a very new area, and but these are considered as a unconventional gas fields. Now, what is the composition? It's a complex mixture of hydrocarbon and non-hydrocarbon constituent, and it exists as a gas under atmospheric condition. Then raw natural gas means the gas which is produced from the wells, that is Mother Earth from geological formation. It typically consists primarily of methane, the shortest and the lightest hydrocarbon molecule. It also contains varying amount of heavier gaseous hydrocarbons like ethane, propane, normal butane, isobutane, pentane, and even higher molecular weight hydrocarbons. Then acid gases like carbon dioxide, hydrogen sulfide, and sometimes mercaptan. Acid gas, when we say, it's a gas which is containing carbon dioxide in a substantial quantity. Then other gases like nitrogen and helium. Helium is also found in good quantities, particularly in the gas fields of Rajasthan, the ONGC field, not the Oil India or what we call is other fields. But in ONGC, that is Barmer and Jaisalmer field, there the natural gases have good quantity of helium, right up to 300 to 400 ppm. Then water vapor and liquid water, that is always associated with the any gas which is produced from the Mother Earth or from the wells. Liquid hydrocarbons and natural gas condensate. Here you can say that liquid hydrocarbons are heavier hydrocarbons which exist at the atmospheric condition as a liquid, like pentanes and heaviers, and there are a good amount of butanes and propanes also. They always have a propensity to go into the liquid phase depending on their phase condition, that is the condition of their temperature, pressure at the pipeline or at a processing condition and other things. Then sometimes mercury is also found in the natural gas. So far we have not come across any gas field in India where any mercury is reported. Let me show you a typical composition of a natural gas from the offshore gas field, the largest offshore gas field, where you can see the methane is around 80%, and heavier hydrocarbons, when we say hexane plus, is about 0.21, because hexane, heptane, all grouped together are this much. Then nitrogen is there, carbon dioxide is about 6%, and H2S is there. This is a sour gas field which is having very high concentration, that is about 300 parts per million, 300 ppm. Then its specific gravity, calorific value, and other things are also given. And just have a look at the processed gas, that gas which goes into the HBBJ pipeline. You can notice the difference is that H2S is less than 4 ppm, and moisture dew point is minus 62. So this gas is bone dry. It is absolutely dry, whereas the gas which is coming from the offshore field is fully saturated with water vapors, liquid water, everything is there, because it's coming and through pipeline transportation. So from offshore field to our shore terminal, so that is having a lot of water vapors and liquid water also. But when it is processed and sent to the pipeline to the end consumer, it is absolutely dry. It is a bone dry, minus 62. It signifies the temperature at which it gets saturated with water vapor, and if the temperature is lowered, the water vapor will start condensing. So under no foreseeable condition the temperature will go down to -62 at any point in time. Then there is a general utilization of natural gas, like industrial maximum 34, then power generation, then residential for city gas distribution, commercial. These are the general requirement, like power, fertilizer, city gas distribution, industrial, petrochemicals, sponge iron. In our economy, particularly in energy sector, the share of natural gas, primary energy sector I'm talking about, the share of natural gas is steadily increasing. Right from 8% in 2009, it is close to around 15%, and it is further slated to increase. So role of natural gas is increasing. Then this is the scenario within the country about natural gas production and consumption. As you can see, the total production in India is 32,876 MMSCM, that is million standard cubic meter in 1819. Then it dropped to 31,184, and again in 2021 it is 28,675. And out of which the major share is produced by ONGC, that is 2021 it is about 21,872 standard cubic meter, million standard cubic meter. And Oil India and private JVs have a very small share. So major producer of gas, natural gas in India is our ONGC. When we talk about the consumption in India, it can be almost double. That consumption of natural gas in India is almost double the production. Like in 1819, it was about 60,798, or we can say 60.8 BCM, billion cubic meter. And in 2021, it has reduced, as you know, because the economy was hit during COVID and the energy consumption also dropped. So gas consumption basically dropped to 61. And the shortfall is met by LNG imports. So almost you can say about 28.6 billion cubic meter was our internal production in India. About 32.9 billion cubic meter is our LNG import. So we are meeting the shortfall by importing. So that is the scenario in the country about oil gas production and consumption. Then the question, are you getting me? I am not getting any response or not. So I don't know whether I am audible to you or not.
Yes, sir, you are audible.
Yeah. Because in between, if you can get, I can get some prompts. So I am sure that whatever I am telling is going to the, because I cannot see the other side.
No, sir, you continue, please. Continue, sir. You are audible.
Okay. Now the basic question comes about natural, why processing? Why processing? That is what we are talking, and that is what is our subject today. That natural gas processing. Why processing? Basically, because raw natural gas, when it is produced at an oil well, be it offshore, be it onshore, and when it is transported to from the field gathering network to any processing station, then it has a lot of what we call it undesirables or lot of impurities. So the raw natural gas as such cannot be sent to any consumer, or it cannot be sent to any long distance pipeline system for the use of end user. So what are the basic objectives of the natural gas processing? Is first thing is to, because whenever it is not raw natural gas is there, it is a mixture. It has a natural gas, it has a condensate, it has a non-condensable, it has acid gases, it has water, and some sort of dirt and solids are also there. So as it is not fit for use by the industry for the transportation. So basic objective of the gas processing is to separate natural gas, then condensate, then non-condensable, then acid gases and water. So this is the prime objective, because the gas which we are producing as such is not fit for even transportation and for the end user. Now we will see largely what are the problems these impurities or undesirables create. First, we see water vapor. It is very common thing because in the oil wells, it is always having any oil well always have a water drive in the reservoir, and whenever it is produced, water and moisture will always be there with oil and gas which is being produced. So it is a most common impurity. It is not objectionable as such, but liquid water, what happens? First thing is that when a pipeline pushing oil and gas, if it has a liquid water, so it will accelerate the corrosion in presence of H2S gas or in presence of CO2. So water is always for any corrosion to initiate, liquid water has to be there. So gas anyway has CO2 and H2S. Both are corrosive when they are combined with the water. And another phenomena which you may be aware is that during the pipeline transportation, because of the expansion, because the pressure drops, the temperature also drops, the cooling takes place. And during this cooling, the temperature may drop down to the level that these liquid water present in the pipeline may form gas hydrates, that is a solid hydrocarbon or ice, and it may block the transportation of the gas in the pipeline. So that is also one of the very major challenge that I can tell you, like from Mumbai High, when the oil and gas is pushed to say shore terminal of Uran, about 250 kilometers, there it is pumped say about 100 kgs and the temperature is about 60 degrees centigrade. But when we receive it at our terminal at Uran or Hazira, the pressure drops to about 60 kg, that is 40 kg difference, and the skin temperature is as low as 10 degrees or 12 degrees. So if it reaches to the hydrate forming temperature, because every ingredient is there, it is a perfect recipe for making hydrates, because liquid water is there, and if the water temperature drops down, so hydrate formation, particularly in the thermowells and other places, hydrate formation will take place, and that will be very difficult to dislodge. So that is why there, as a matter of common practice, in this pipeline from the production site to the processing site, always it's a practice to inject some dew point depressant, DPDs, or we are using antifreeze. And glycols are the most common, or methanol is the most common antifreeze which is used, which can depress the hydrate formation temperature. So that is there is an entire phase behavior of water hydrocarbon system, and given the composition of water and given all those things, when we can work out and can find out what is the hydrate formation temperature, and if our skin temperature is nearing to that temperature, we have to depress it. Accordingly, it is planned and it is done as a matter. So that is why, and same phenomena is there from the processing side to the cross-country pipeline. If water drops, then if liquid water is there, the first thing is it will initiate corrosion and then a hydrate formation will take. So it is a very big thing that we have to take care of this water. Then H2S and CO2, as you know, both are corrosive. And apart from being corrosive, H2S is very poisonous and hazardous gas. Every country has some limits fixed that the H2S in the natural gas should not cross beyond this limit. Then it's a sort of in steel and other things, it promotes or initiate stress cracking also. So H2S, and similarly CO2 also. CO2 also is a corrosive one, but for CO2 to be corrosive, a higher concentration is needed that compared to H2S. So both H2S and CO2 are to be taken care of. As far as H2S is concerned, that is to be removed and brought below A, like you have seen in the case of processed gas. It is desirable, and as per the PNGRB guideline, also it should be less than 5 ppm. So see, H2S has to be taken care of, very stringent requirement. For CO2, the requirement is not that stringent, because for the CO2 to become corrosive, the partial pressure of the CO2 has to be more than 30 psi, and water has to be there. So if the water dehydration is taken care of, then CO2 may not, because for certain industries CO2 is desirable. But our PNGRB guidelines has already fixed the limit of CO2 and other non-hydrocarbons. Then as far as liquid hydrocarbons are there, the liquid hydrocarbons during transportation long distance, they reduces the pipeline flowing gas. Suppose if the gas transportation line is there and in between if a slug is formed where the liquid hydrocarbons, where the heavier hydrocarbons are getting dropped and getting accumulated in the pipeline carrying capacity is reduced. And another thing is that there is no provision in between that how to handle, how to, because you cannot drain it, these liquid hydrocarbons as this. So liquid hydrocarbon has to be controlled. It depends on what is the end user requirement and what is the agreement between the seller and buyer. So liquid hydrocarbon also has to be taken care. And these liquid hydrocarbons are also to be taken care in the gas pipeline, because from these liquid hydrocarbons we produce value added products like naphtha, like LPG and other things. So these liquid hydrocarbon at the first processing terminal, they have to be taken care. Then this is a PNGRB gas quality specification for transportation through long distance pipeline, PNGRB regulation. That hydrocarbon dew point should be maximum limit is 0, water dew point is 0, hydrogen sulfide ppm weight is 5, total sulfur, carbon dioxide maximum is 6, total inert maximum is 8, temperature is 55, oxygen. So you can see these are the reasons why the gas needs to be processed before it is being of any use, economic use, before it is being transported and other things. I'll discuss about hydrocarbon dew point a bit about when we will be talking about dew point depression unit, DPD. Water dew point, you know that it is the temperature at which that system, that gas water system gets saturated with the water vapor, and any further drop in the temperature will lead to the condensation of water vapor in the system. Hydrogen sulfide, total sulfur, and these are the limits which one has to abide, every producer has to abide if it has to push its gas in the national pipeline or cross-country pipelines. Then the various general process modules for the natural gas are, the first unit of the module is the physical separation of the distinct phases, because the pipelines, normally these pipelines are a multi-phase flow is there, crude oil is there, gas is there, water is there, like crude oil is there, condensate is there, gas is there. So first thing is that your physically distinct phases हैं, like gas, liquid hydrocarbon, liquid water, solids, they have to be removed at the receipt, at the entry point, what we call is a battery limit of the plant. The first thing where the gas or condensate is received from the offshore field, there it is to, the first thing is to be taken care is to separate these different phases, gas, liquid hydrocarbon, liquid, before it processed further. Then the next step processing is gas sweetening, because I am talking with respect to if the gas sweetening, when the CO2 is, when the hydrogen sulfide is in significant concentration, it is to be sweetened for processing further. So the very important process is gas sweetening. In the gas sweetening, depending on the end use, what is our cleanup target that is decided. Just to give you an example, like the gas which is received at Hazira plant is from South Basin, Tapti field and nearby field, is a sour gas. When we call sour gas, it means the H2S is more than 4 ppm. As you have seen, about 300 ppm H2S is there. So that sour gas, our primary objective at Hazira plant is to reduce the H2S concentration below 4 ppm. Whereas when we talk of, say, the associated gas processing at Udan plant, There our primary objective is to take care of CO2 because their H2S is not that much, but CO2 is very high there. And why we have to reduce CO2 is because the further downstream processing, the cryogenic process is involved, like for the recovery of C2C3, that ethane propane. There the temperature goes to say minus 66 degree, minus 100 degree. So there, if the feed gas is not, with the CO2 is not brought below 50 ppm level, there the solid CO2 may be formed. So it depends on what is the ultimate purpose of gas sweetening, and accordingly the process and all those things are decided. But it is driven by the fact that what is the purpose, what is the end use of that gas, and what are the cleanup targets. Then gas dehydration module, as you know, gas dehydration, because during the process of sweetening, which is mostly using the aqueous solution of amines, different type of amines or any other solvent, the gas is fully saturated with water vapor, because with that the temperature is also high pressure, low pressure is there, so gas is fully saturated with water vapor. So before it goes to further process units, it is to be dehydrated enough so that it goes to further processing units. So gas dehydration is there, the gas dehydration module. Then dew point depression, as I talked, because natural gas liquid recovery is there. Whatever is the heavier hydrocarbons are there, C3, C4, C and higher, they have to be recovered in that module. Then next thing is that condensate, because gas and condensate both are coming from the offshore. So condensate also has to be stabilized, fractionation module. Then desulfurization of acid gas. Desulfurization of acid gas, when we talk, because when we sweeten the natural gas in our gas sweetening unit, the resultant gas are, one is sweet gas, another thing is the acid gas. Means after scrubbing the all the CO2 and H2S, that gas is vented. So that is called as acid gas. But that gas contains very high concentration of say H2S, more than 10,000, 20,000 ppm, and that as such cannot be vented in the atmosphere because of the regulations, and otherwise also it cannot be vented in the atmosphere. So that acid gas, which is having large concentration of H2S and CO2, has to be treated before it is finally disposed of. Like it is disposing the effluent water, so this effluent gas during the process of sweetening has to be treated before it is vented. So there the process is to recover the sulfur, that convert that H2S into sulfur, and that sulfur is a economic value also, and then only it can be ultimately disposed. These are the general process modules of a gas. Now I will, instead of these general process modules, I will tell you the case study which is very apt for the Hazira plant, because Hazira plant is one of the largest SAR gas processing plant in India. It has a design capacity of about 46.9 MMSCMD. It is processing 33 to 35 MMSCM gas per day and about 5,000 cubic meter of condensate per day. So that is the general background of the plant. You see, I was telling about these. These are the field in Baseen field, which is the largest gas field in the India. Then this is Tapti field. So from Baseen field and Tapti field, there are two large process platforms, which we call as BPA and BPB. So two pipelines under sea. These two pipelines are emitting from there. One is 36-inch diameter and another is 42-inch diameter. They are on the seabed, and the length of the pipeline is about 242 kilometers. These are the trunk lines from in which these gas and condensate produced by Baseen field and Tapti field and other smaller field is pumped. And from Baseen field, it is coming to Umbarat, that is a place near Surat, which is the landfall point. These from the seabed, it is now on the land it is coming at Umrat. And Daman field also recently started producing, that is also pumping in these pipelines. Daman is also producing gas. So this is about 242 kilometer length, two pipeline. One is 42 inch, another is 36-inch pipeline. From this offshore field, that subsea pipeline is coming at the surface near Umrat. So this is the now at Umrat there are two valve station there, and this pipeline undergoes under the two what we call is sea, that Mendola and Tapti. These two rivers are there, and these are the various valve stations. And now it is coming and joining at Hazira plant. This is Hazira plant. Why it is very important for this is the energy lifeline of North. All of you must have heard about HBJ pipeline, Hazira Vijaypur Jagdishpur pipeline. That pipeline is now operated by the Gas Authority of India, and it is more than 3,300 kilometer long pipeline, which is carrying gas to about 6 states throughout the India. Our plant, Hazira plant, is the mother plant of this pipeline. So we are giving gas to this pipeline, and just opposite Hazira plant, gas, this GAIL terminal is there. From there, GAIL is taking, we are transferring it to in that pipeline to GAIL, and further onwards, GAIL, this pipeline transportation that GAIL is looking at through this pipeline, and it goes all the way up to Delhi, Haryana, and the pipeline length is about 3,300 kilometers. Now I'll show you the various process. Excuse me. A block diagram of various process modules, or what we call is process flow. So the gas and liquid both are coming first to the gas terminal. That is the battery limit, what is called gas terminal. In the gas terminal, the purpose is to receive and separate sour gas and associated condensate from the offload. That is the purpose of the gas terminal. So from the gas terminal, there are two streams. One is of gas, another is of condensate. The gas goes to gas sweetening unit. That sour gas which is coming out, which is being separated at gas terminal, it goes to gas sweetening unit for removal of H2S, and we are using MDEA process by selective absorption in the methyl diethanolamine, that GSU. Then from GSU, that gas goes to gas dehydration unit. As I explained, that because in the process of sweetening, it is fully saturated with water. So we have to remove it, all the water, moisture, water vapor, everything. So from GSU, it flows to the GDU, gas dehydration unit. And in the GSU, whatever is the vent gas or whatever is the effluent, what we call acid gas, that goes to the sulfur recovery. And from sulfur recovery unit, we get a sulfur, solid sulfur, and then it is vented. After recovery of sulfur, the resultant gas is vented. And that gas, that sweetened gas or sweet gas we call, goes to GDU. And at GDU, it is dehydrated, and process I will briefly explain afterwards. Then from GDU, it goes to DPD, the dew point depression unit, removal of liquid hydrocarbon to make it suitable for transportation through the, now the pipeline length has been increased to 3,300 kilometers. Because during the process of transportation, liquid hydrocarbons may drop out in the system, and that can create operational problem, that can reduce the pipeline carrying capacity and other things. And in the dew point depression unit is designed so that there is a, because what happens is along the HBJ pipeline, GAIL has also put up some LPG plant or some petrochemical plant. And in LPG and petrochemical plants, they require some concentration of higher hydrocarbons like C3, C4 and other. So the DPD is so designed that we cannot remove all the heavier hydrocarbon here. Some amount of heavier hydrocarbon goes, and that is what the condition of hydrocarbon dew point is there, which is as per PNGRB guideline. It has to be maximum, that is 0 degree centigrade. Whereas we are trying to maintain here, say up to -5, so that condition is also met. Then at sulfur recovery, as I explained, is we convert hydrogen sulfide to elemental sulfur for environmental protection, and then from GSU, the part of gas comes to LPG plant. From the GSU, the sweet gas is there. One part goes to GDU, and another part comes to LPG plant, where we produce LPG and naphtha from the sweet gas by cryogenic process. Here the LPG is produced using the cryogenic process, and that also I will briefly explain. Then the condensate. This is regarding the pathway of gas. Now from gas terminal, another stream, that is liquid stream, that is condensate. It first comes to condensate fractionation unit, because that condensate is also SAR condensate, having H2S and other things, and lighter fractions are also there, because it is at, say here the system is about, say, 60 kg or 64 kg. So of course some of the lighter will be always there, what you call is dissolved in the condensate. H2S also will be there. So it comes to condensate fractionation unit, and in condensate fractionation unit we fractionate the associated sour condensate. In the process of fractionation, what we do is we strip the lighters, that is C2, C1, C2, C3, and the H2S, and the remaining one we take it for the LPG recovery. So there are two streams which goes to, one is gas, that sweet gas from this place, it goes through cryogenic process, and the sweet condensate after stripping lighter hydrocarbons and H2S, there also LPG production is taking place. Then after stripping the condensate of the lighters and H2S, and then recovering LPG is basically C3 and C4. So after doing all these things, the remaining condensate, we call it NGL, that goes to kerosene recovery unit, where various value-added products like naphtha, like kerosene, ATF, HSD, HFHSD, all these things are produced. Then the LPG here produced by the CFU. In the CFU, whatever LPG we produce, that also has a higher concentration of H2S, because H2S here produced by the CFU is having higher concentration. So because LPG also has a very strict requirement of, say, 4 ppm and of H2S, so it goes to caustic wash unit, where using the caustic wash process, this H2S is removed from the LPG. Then only it can be sent to consumers. So this is a process flow where various process modules, how they are interrelated, interlinked in the gas processing plant, a typical largest gas processing plant, that to SAR gas processing plant is explained. Is there any feedback or anything which I would like to know, which I can clarify further? Hello?
So please continue, sir. Please continue. I will ask question at the last, at the end of the session.
Okay. Now, first thing is that at received, as I said, is a gas, gas received, that is gas terminal. I am giving you one simple cross section of the system which is there, which we call a slug catcher. It is nothing but a pipe, a large pipe of about half a kilometer length and about 48 inch in the diameter. We call it fingers. So, and they are slanted, as you can see, they are slanted. So likewise, there is an entire area where these 24 fingers are there, like this, and they are basically acting as a separator. That condensate and gas separation is takes place. Like you can see, it is just a cross section of a single pipeline. It is a huge area where these things are laid out. That 24 fingers are there, and each finger is having about half a kilometer length, and about 14 pipe diameter is about 48 inch. So they are separate. They separate also oil and gas, and they store the condensate. Also store in the sense there it is temporarily stored, and then it goes. It's a continuous process. From there, the condensate goes to through metering and through thing. It goes to CFU. That is condensate fractionation. As you can see here, the risers are there. This is the slope is there. At various places risers are there, and they are all equalized, and these risers the gas is removed. So this 16-inch riser, then 12-inch riser, 8-inch riser. So all these, the major separation takes place here. The gravity separation there, it is coming. The gas goes here, and whatever is remaining gas, it goes here. The first thing is that condensate and gas is separated here in the slug catcher, and from there the gas further goes to the molecular sieve dryers, not dryers, that filters are there, then other things are there, and then through metering it goes enters into the plant. Similarly, condensate also through metering it goes into the condensate fractionation unit, and the gas goes to the gas sweetening unit. Now come to gas sweetening unit. The process of gas sweetening, as I explained here in this particular Hazira plant where we are handling sour gas, our purpose is to remove the H2S and bring it below the stipulated by the government authorities, by the regulatory board, below 4 ppm, whereas in our inlet we have more than 300 ppm. So there are various technologies available that is we are using by amine scrubbing, and most main alkyl amines which are used in the gas sweetening industry are MEA, monoethanolamine, DGA, diethanolamine, diisopropylamine, methyl diethylene, that is MDEA. So we are using MDEA process, and why we are using MDEA process, and what are the relative advantages? It all is depending on what is our purpose. We are sweetening the gas for which purpose? What are our input condition? What are the quality of input gas? What are the pressures, and what are the quantity? All those things. There are various factors, the design basis, which dictates that which one is to be utilized. So we are using the MDEA, as you know. Our purpose is primarily to remove the H2S. So the general process chemistry is that MDEA, being a tertiary amine, it reacts instantaneously with H2S through a proton transfer, and during the regeneration process, again this H2S which is trapped at the MDEA is released, and MDEA becomes free. And here it is typically the pressure swing is there, because this absorption takes place at high pressure and low temperature, whereas the desorption takes place at low pressure and high temperature. And MDA being tertiary, I mean, it is the reaction is very instantaneous with H2S, but there is a competing reaction also, because in the gas we have CO2 also, and this is being amine, it reacts with the CO2 also. So what happens is it reacts instantaneously with H2S. This reaction is very fast. As I've told, by proton transfer, hydrosulfide is made. CO2 can react only, first it has to dissolve in the water to form a bicarbonate, then acid-base reaction takes place, and then bicarbonate and amine carbonate is taking place, and then only the removal is there. So this is a slow process. This is a slow reaction, but nevertheless, this also takes place. So along with H2S, there is always some co-absorption of CO2 also. And that is what is very interesting and very tricky, that all the time, because it's a continuous process. This is not a batch process that one particular quantity we process and then control and then move away. It is a continuous process. So this competing phenomena are, because why we are choosing MDA, because there is a selective, like there is a kinetic selectivity for the H2S compared to H2 CO2. Whereas if you have to remove CO2, you have a different amine, where the kinetic selectivity favors the removal of CO2. So that is the purpose of selecting MDA, because it is a tertiary amine, MDA. CO2 being a larger molecule, there is a steric hindrance also. The reaction is not instantaneous. It's a slow process, but nevertheless it takes place, and there is always some co-absorption which we have to monitor and control. Plus there are various factors which determine that when the kinetic selectivity favors CO2 or kinetic selectivity favors H2S. That is all about that. Process chemistry is very intricate, and one has to understand thoroughly, then only it can be successful. Like I'll show you a cross section of the absorber, that high pressure absorbers. There are various field equipments and all that, pressure valves, knockout drums, and other things. Usually, whenever a gas comes from the CFU, a knockout drum is there. So whatever is entrained, the liquids are there. They are removed here. Then basically here in this absorber column, there is a counter current flow. Means gas is entering from the bottom, and the amine, like his amine tank, is amine is entering from the top. Now these trays, and where the amine can enter and where the contact can take place, that contact time, that height, everything is optimized depending on what is the concentration of the various components in the CO in the gas, and what are the other parameters, what are the this is very it has to be controlled. So there, that is a very sort of interesting process, where suppose if this H2S loading is very high, then the contact time will be different. If the H2S loading, because the plant is designed and this absorber is designed based on certain input criteria. So if the H2S loading is very high, then accordingly one has to increase that contact time. Once the H2S loading is less, because if you increase or decrease the contact time, it may have some other implications which are not desirable. So in general, these are the process controls given, which is to be determined in the process. So this is basically a counter current flow is there, where gas enters from the bottom and amine solution comes from the top, and the mass transfer takes place. CO2 and H2S, basically H2S from the vapor phase goes into the liquid phase, and the gas, that is what is called the sweet gas, comes out of this, and it goes to the knockout drum. Whatever is the entrained thing is there, that is removed, and then this sweet gas goes to gas dehydration unit. This amine, this amine we call rich amine, because why rich amine? Because it is all loaded with H2S and CO2. This rich amine goes to for the regeneration, and in the regeneration, what happens is a pressure is reduced. It is almost atmospheric pressure, whereas there in the absorber column the pressure is 60 kg. You see, pressure is 60 kg, and the amine temperature is also controlled, because there are a lot of heat exchangers are there, plate heat exchangers, other heat exchangers are there, and it is always desirable to control the amine temperature, that some solution temperature, because if temperature is more, it will have a different dynamics, because its viscosity will be different, its solubility will be different, it will have sort of it will be favoring more of a CO2 absorption than H2S absorption. So there are many intricate things which is to be controlled and which is to be understood thoroughly. But in general, within the given time, everything cannot be explained in detail right now. In a regenerator column, it is pressure swing is there. I have shown you directly the regeneration column, but intermediate there is a flash drum also. From 60 kg it is flashed to about say 6 kg, and then it comes to 1 kg. That is atmospheric pressure, where it is flashed, and steam stripping is done to remove H2S from the lean gas, from the rich amine. Amine flows from the top, and steam through steam stripping is done, which removes whatever is the absorbed H2S is there, and the amine, the resulting amine is free from those things. So again we call it a lean amine. Lean amine means there is minimum loading, excuse me. Lean amine is with respect to the H2S and CO2. The loading of H2S and CO2 is minimum or no loading. Rich amine means it is fully loaded with the absorbed H2S and CO2. So that is how it is there. Then this gas which is released from the rich amine is acid gas. This is what is called acid gas, which is having mostly the CO2, H2S, and some amount of hydrocarbons are there, though our endeavor is to control the release of hydrocarbons, because that is a loss, that is a value added product, that hydrocarbons, if they are going to acid gas. But nevertheless, some amount of hydrocarbons, say about 1% or below, always it is having about more than 90% CO2 and about 10,000 to 20,000 ppm of H2S. Then through various processes and other, it goes to sulfur recovery unit, which we will see later on. And this lean amine again goes to the amine tank, and from there it goes to the absorber. Now the other very important thing is there, that that MDA which is used, its hygiene is very important. MDA hygiene, when we call it, says it has to be very clean. Clean in the sense that if any particles are present during this process, because all these pipings and everything is there, there is every chance, and there is for entrainment of fine particles and other things coming from the offshore or coming through these pipelines and other things. So these small particles, they create havoc with the system, because what happens, they promote foaming, and once there is a foaming in the absorber column, the entire system, there is a serious process upset, and foaming is there, a lot of liquid carryover is there. So maintaining the amine hygiene is extremely important in the gas sweetening, and there are very elaborate arrangements for maintaining the hygiene of the amine solution, that MDA tank. One thing is that it is blanketed with inert gas, because if it is exposed to, say, atmospheric conditions or so, it will be oxidizing it, and its strength will reduce this amine solution. Another thing is a slip stream is there from this tank, which is passed through continuously. A pre-coat filter is there, where the particle up to the size of 1 micron is removed. Then we have a charcoal bed, where if there is a traces of hydrocarbons, liquid hydrocarbons which are coming, they are also taken care. Then there is a cartridge filter, where any dust, dirt, particle or anything is there are removed. Then the regeneration, I've already told, this is a filtration system. Then as I have told, that there are various factors like contact time, amine concentration, lean amine temperature, filtration, which I have explained in between, that how important they are. Then filtration may pre-coat filter like iron sulfide and iron carbonate, charcoal and cartridge are there, which are taking care of all entrained microsolids and other things. They are the critical parameters which has to maintain, like amine concentration, that pH, residual H2S concentration, residual CO2. There are a lot of other things. Is very briefly I have just given you. Now comes to the gas dehydration. Purpose, as I have already told you, there are 3 basic reasons for dehydration. of the natural gas stream. One is to prevent hydrate formation, as I explained, then to avoid corrosion problems. So what process is obtained normally for dehydration? It's also downstream processing requirement in most processes. For example, you know about CNG and LNG, the liquefied natural gas and compressed natural gas. In liquefied natural gas, it is say the temperature goes to say minus 161 degree or so. So if your feed gas or this natural gas is having even traces of water vapor, it will disrupt that process. So for the CNG process, for the LNG process, one has to be, the gas has to be bone dry. So depending on what is the ultimate application or usage of that gas, this gas dehydration is very important. For example, in LPG, when we produce LPG from the gas through a cryogenic process, in that case also there the temperature may go up to minus 50, minus 60 degrees centigrade. So one has to be very, the gas which goes to the LPG recovery through a cryogenic process has to be bone dry. It has to be, all the moisture, traces of moisture has to be removed. Absorption and adsorption processes are there. Both processes we use at Hazira plant. The purpose is different. The basic principle is that hygroscopic liquid is used to contact the wet gas to remove water vapor from it. TEG is the most common solvent which is used. TEG absorbs water from the gas until the equilibrium partial pressure of TEG and water. Here also counter current flow is there. TEG is coming from the top and gas is going from the top bottom, and they mass transfer takes place. All that moisture, TEG being hygroscopic in nature, all that moisture is absorbed, and when there is equilibrium partial pressure of TEG, this thing, the TEG is again regenerated, same almost similar process that we for gas sweetening. And this process is more favorable at lower temperature and higher pressure. Another is dehydration process, is adsorption process using solid base. This is used when very low dew point requirement is there. For example, just to give you an example, the gas after dehydration process is having a moisture dew point of say about minus 40 or minus 42. Whereas the gas after the dehydration through a solid bed, that is molecular sieve which we use in the LPG plant, molecular sieve bed has a moisture dew point of minus 62, minus 63, even minus 66. So that level of dryness is required because the temperature at the downstream where LPG recovery takes place reaches up to say minus 40, minus 50, minus 57. So that is the purpose. And just again, simple thing is there that TEG is coming from the top, gas is going from the bottom, and mass transfer takes place, and water is removed. Then this is a regeneration. Here in the regeneration, the steam stripping is done. The TEG, that steam stripping is done, and that moisture is removed from TEG, and that TEG again goes for the regeneration part. This is very complex process flow diagram of LPG production from the gas, particularly sweet gas, but conceptually I'll tell you all our other things are there. These are three molecular sieve dryers. These molecular sieve dryers, when the sweet gas comes from the GSU, they remove all the traces of moisture, and if any H2S residual is there, that also is being removed. Then it goes to the filter, because see, molecular sieves are there, some and operating at about 60 kg or so with a high flow rate. There may be some attrition, so some finers may get carried over. So there is a filter is here, gas filter is there, so that takes care of those things. and then it goes to the cold box. Basically, cold box is a system where the heat exchange takes place between the colder stream and the hotter stream. And from the cold box, that gas goes to the, after exchanging the heat, is goes to the first stage separation, where whatever liquid is formed, that is removed, and the gas again goes to the chilling process, where it is used as a turbo expander, the expander compressor, where the pressure is dropped. Using this turbo expander, it is chilled up to minus say 50-57 degree, and then again it goes to a separator. The gas is removed and the liquid is there. So these two liquids from separator 1 and separator 2, after the heat exchange here in the cold box, they come to the light end fractionator. They both, this is the light end fractionator which strips C1, C2 and some amount of C3 from these liquids. So C2 and C3 is removed from this liquid, and the remaining one, after stripping that C2, C3 and lighter C1, C2, C3, basically light end fractionator, the top gas consists mostly of C1, C2 and C3. And we monitor the loss of, there should not be ideally any loss of C4 here. So this should not have any. Madam. Okay. Okay. Thank you. Okay, I will just quickly sum it up. So this is the process. It goes to light end fractionator, then it goes to LPG column. Condensate stabilization, as I have already explained the purpose of stabilization of condensate. And here also the process is, first it goes to a stripper column where the lighters, that is C1, C2 and H2S, are stripped, and the bottom goes to for LPG recovery, where LPG is recovered and remaining one is called NGL, which goes for the kerosene recovery unit. In dew point depression, we use propane chiller, that from GDU, gas dehydration unit, whatever gas comes, it passes through a heat exchanger where propane chiller is used, and this resulting gas goes to the that condensate from this recovered from this DPD process goes for LPG recovery, and the gas goes to the consumer. Then in sulfur recovery unit, it is as I explained, is very important part of gas sweetening process. Here we are using, see, you can see the H2S is about 10,000 to 12,000 ppm, whereas vent gas meet is required to be below 30 ppm. The sulfur recovery, we are using liquid catalyst, that is low-cat process. It's a proprietary process of Americam. Yeah, these are the chemicals which are used for the liquid catalyst reduction, liquid catalyst process. Basically, this is the ARI3, this is iron solution in a chelated form, then chelon, that is chelate solution, surfactant, bactericide, defoamer, and KOH. The reaction, the chemistry is also very interesting. Absorption means H2S is dissolved in first water, and then in two stages it ionizes to give a sulfide ion, and it is dependent on the H2S partial pressure. Solution pH here, pH is most important, because once the H2S goes into the liquid and sulfide ion is formed, it is an acidic moiety, so solution pH reduces very speedily. And once the solution pH is less, the reaction will be, the H2S breakdown will not be there. The ionization of H2S will not be there. So buffering is done here. So maintaining pH is extremely important. That is why KOH is used to buffer this solution. So that is why it is very important to maintain the pH all the time here in this system, because then only the reaction will always be favoring in the forward direction. Then sulfide oxidation is done using the iron solution, that is ferric. It transfers the proton, makes the solid sulfur, and ferrous iron is formed. Here the iron is used as a reagent which transfer the electron. It works as a catalyst also because again it is regenerated back, and 2 moles of iron is required per mole of sulfur. Then iron, that ferrous iron, is oxidized back to the ferric iron by air taking oxygen from the air. It is again, and this is the overall reaction. Here it is very interesting because the iron, why chelated iron is used, because iron as such has a very low solubility in water, about 4 ppm. But when chelated iron is used, it is having solubility of 40,000 ppm, like 4%. And this also to remain this iron, the ferrous iron, again to oxidize into the ferric iron by using that atmospheric air oxygen. This is also a very controlled way. Thank you. That's what I wanted to give you a brief outline. Though the entire thing is very interesting and it takes it's a full course in itself. But I tried to make the maximum of it. If you have any questions, you are welcome.
Yes, sir. I want to know one thing. What are the criteria of storing natural gas in reservoir?
So for that, storing means it is already there in the reservoir. You drill it and then you produce it, exploit it, that natural gas. Let me tell you that oil well is there. The crude oil may always, you say it is same family of hydrocarbon from C1 to say 1 to C120 or higher. So the higher hydrocarbons say are your crude oil are always, which are liquid, are higher hydrocarbon complex mixtures there. So gas is always dissolved there in that oil, and if the gas is not dissolved in the oil will not flow. We call it dead oil. It gives the mostly the energy drives for that oil to come to the surface. So it is already what we call in oil reservoir is a trap. Within a trap, geological trap, it is stored. And when you drill it, when you open that, it flows, and it is a controlled flow. So it is stored in a natural reservoir. It's not that it is not a man-made reservoir. It is a natural reservoir which has been deposited over the millions of years. And in the geological term, let me tell you, if any reservoir is say about 23 million years old, it is called younger. Imagine 23 million years old means is a younger reservoir. So that is the kind of time scale we talk in the geology. And about, I think you got it, or should I explain it more?
No, sir. No, got it, sir.
So
Okay, I would like to thank you, sir, for your valuable time, and I look forward to our next meeting. Thank you very much, sir.
Thank you.
लीव कर दो सर, बीच में ऐसा बटन होगा कॉल ऑफ करने का, वहां से लीव कर दो सर.
हाँ, लीव कर दिया.
ओके, थैंक यू सर.
थैंक यू.